Let's think about what the harmonic oscillator solutions tell us. So the first thing we know is that since the energy of any V level is V plus a half times omega sub E, we can see that the difference between any two adjacent energy levels is just going to be equal to omega sub E. And so to get from one energy level to the next, it's always a constant. It always involves going from one energy level, adding omega sub E of energy, and getting up to the other energy level. So this difference is always omega sub E. And remember that omega sub E was h bar square root of k over mu. So we can show that this has units of energy. And so the photon required to make this transition, so the energy of the photon has to equal the energy of the gap. And so h nu has to equal h bar over k mu, or nu equals 1 over 2 pi square root of k over mu. And so this has units of frequency, and it's that frequency that the photon has to have in order to make this transition. So we can think of this as the photon having the same frequency as the frequency of the vibration that we're looking at. And when those two frequencies match, we get resonance, and the photon is able to be absorbed, causing the diatomic molecule to transition from one vibrational level to another vibrational level, where the amplitude of that vibration is now larger. Let's take a look at what the wave functions look like. So our first wave function is this Gaussian function multiplied by the first H0 Hermite polynomial, but that first polynomial is just equal to 1. And 1 times anything is just equal to 1. And so this first vibrational level wave function is just a Gaussian function. If we look at the second one, we have a first order polynomial, and a first order polynomial is going to have a function that is just a straight line with a particular slope. So if we multiply the green and the yellow together, we're going to have something that is negative in this region, because a negative times a positive is negative, and something that's positive in this region, because positive times positive is positive, and it's going to go through 0 right where the root of this polynomial is, because 0 times anything is equal to 0. And so if we draw what that looks like, we expect it to be 0 at 0, negative for values below, positive up here. And so that's what our second wave function looks like. Then if we look at the third wave function, we have a second order polynomial, which is 0 at minus 2, and a second order polynomial is just a parabola. And so if we multiply those two together, we're going to be positive over here, negative in the middle, because a negative times a positive is negative, and then positive back over here. And we're going to have roots at the roots of this parabola. So we would expect this wave function to look like this. And so we can draw these wave functions by just thinking about the two functions that are multiplied together. Now let's take a look at some interesting features of this function. So notice that my functions leak outside where the potential is. So our particle is able to tunnel past that potential barrier and get outside into the classically forbidden regions. And it's not just an artifact of how I've drawn these wave functions. This is actually how this works. So in the harmonic oscillator, the quantum mechanical harmonic oscillator, we say that the particle has a probability of being at distances that are beyond what we call the classical turning points of motion. In a classical harmonic oscillator, we have the motion such that when we are at the equilibrium distance between the two masses, all of the energy is kinetic energy, because at that point the potential energy is zero. And then as the bond stretches in either direction, right, then the potential energy gets bigger and bigger until we reach the total energy of the system. And when we get to the total energy of the system, if the potential energy equals the total energy, then the kinetic energy is zero. And so at these points where the total energy equals the potential energy, the particle stops, zero kinetic energy, stops moving, turns around, and goes the other way. So at these points where the total energy equals the potential energy, we have zero kinetic energy, and those are called the turning points of the classical motion. So turning points are where the potential energy equals the total energy. And so we can figure out where these turning points are, because we know that we have 1/2 kr squared has to be equal to our total energy. And our total energy is V plus 1/2 times omega sub E. And so we can solve for the R values that give us these turning points for each of the different quantum levels. So R squared is V plus 1/2 omega sub E times 2 over K, or R, the turning points, are plus or minus square root of 2 V plus 1/2 omega sub E over K, or we could write that as plus or minus the square root of 2V plus 1 omega sub E over K. So it depends on that spring constant, how stiff that spring is, how much it's going to stretch before it snaps back again. And those are called the turning points. So those are the turning points of the motion. And we can see that, in fact, our wave functions show us that there is a finite probability of being beyond those turning points of motion. There isn't any classical analogy to this, and this is a purely quantum mechanical phenomenon. And again, remember that when we're in those classically forbidden regions, we formally have a negative kinetic energy, which doesn't seem possible. Another interesting result is to think about where we expect to find the particle most often, or the highest probability of finding our system. So when we're in V equals 0, we're in the ground state of this, we expect that the particle will be most often at its equilibrium position, because we have the maximum of the wave function, which means that the wave function squared will be a maximum at this point. Initially, that seems to make a lot of sense, because we would expect to find the particle at its equilibrium position. And in fact, the average will be at that equilibrium position no matter which wave function you look at, because these wave functions are symmetric around y equals 0. And so there's an equal probability at negative y and an equal probability at positive y. And so the average will always be at that equilibrium position, which makes sense. But if we think classically, at this equilibrium position, that's where the motion has the highest velocity, has the highest kinetic energy, and therefore the highest velocity. At the turning points, it has 0 velocity, and so actually it spends the most time at the turning points. And so we might expect to see that the particle would in fact have the highest probability of being found at the turning point, since that's where classically it would spend the most time. If we examine wave functions above v equals 2, so we have here v equals 3, v equals 4, and v equals 5, and we look at the probability, psi star psi, we can see that, in fact, as the quantum number gets higher, that we actually have a global probability that is closer to the classical turning points of motion. And so the probability at the classical turning points is actually the global maximum. And that would match with our idea of the classical motion, where the particle spends the most time at the turning points and the least time in the center. So in spite of the fact that this ground state doesn't show that type of motion, there is, as we get higher and higher in energy, it begins to look more and more like that classical solution where the particle is spending more and more time near the turning points and less time in the middle. So as we go up in energy, our system becomes more and more classical, and it's really down in those lower energies where it doesn't follow that classical understanding of harmonic motion.